curriculum in geological sciences. Edwin's working on the revisions of that right now. And we haven't really developed at all the career of geological engineering. And so, it's something that we intend to do along the way. And I'm telling you, most of you might have heard this already. What we want to do for now in the next couple of years until we have a full career in geological engineering, and anyhow, what I want to do permanently is incorporate engineering into geosciences in a way that isn't done, for sure not in the United States, but I don't think in curricula in geosciences anywhere in the world. So we want to have special courses designed by engineers in which we can teach, electrical engineering to geoscience students, so that our students are not just capable of great theoretical understanding and knowledge about the world around them, but they also know how to make stuff and fix stuff and invent stuff and innovate stuff. And that's embedded within the curriculum at Gachai. We're going to have some special courses designed by special people. And the kind of person that we want to have do that is Alex Jurgis, who's, you can tell, it looks more like it when he has his sunglasses on. He's a protege of our member of the Commission, Jose Andrade. When he was up with his sunglasses, and I saw him from a distance, I thought it was Jose. And, Alex got his undergrad degree in civil engineering and his master's degree in civil engineering from the University of Cuenca, great university. It's a beautiful place too. I found out last week. Really great to be there. And then got his PhD degree. I think you got your master's degree and PhD degree in applied mechanics at Caltech under Jose. And he had a side project. I think maybe the side project is going to be, well, anyhow, he's going to be probably showing us some material from the side project.
Sure,
so
I will.
He's really a civil engineer, interested in granular materials. It's the kind of stuff that we would do in geological engineering. And he's the kind of person that can inform us a lot in geological sciences and inform our students. And so it's a pleasure, great pleasure to have you here. Nice to meet you. And
thank you.
Thank you.
Thanks all. Well, thanks everyone for coming and for having me here. I've been having tons of fun talking to you guys along the day. So let's see if I don't get to bore you too much talking about my stuff. Well, Sigmund Freud used to say that, a psychoanalyst talking to a psychologist is like an elephant talking to a dolphin. Anyway, they are animals and things like that, but they have nothing to do. And well, I'm not a geologist by myself, but I've been working with that stuff, and engineering and geology, civil engineering, and so on, so far are related somehow. And what's good about Caltech is that the environment is a small school. There are very few people there. The environment is so small that we tend to collaborate within departments and fields and everything. So I'm very used to that kind of collaboration. So let's see how it can go. And let me talk about my research. Let me give you a brief prelude in background on granular materials and modeling. So, granular materials can be found everywhere around the Earth and even outside of Earth. And they can behave in many, many different ways. For instance, they can behave like solids. And you can stand on top of them without sinking. They offer a strength. They also can behave like fluids. And you can build these cute sunglasses. And you can use them in many different industrial processes as well. Also, they can behave like gas. And you have these sandstorms that affect many populations around the world. And finally, they are very important in cosmic events. So they are part of rings surrounding planets. They have become very fundamental for NASA the last 5 years or so, since the Spirit back in 2009 got stuck in Martian sand. And now they are worried about that, so they want to understand the behavior of what they call regolith in general. So this is the big picture. And in terms of modeling, some of you may be familiar with this picture. You have this bar, metal, wood, whatever, and you pull it. And by pulling it, you can build this curve, which is a strain versus a stress. And in this way, you study the strength of these kind of materials. So in granular materials, you can do a similar thing, but this is that you need to put some pressure. You need to confine the material because they don't offer self-confinement usually. So you need to pre-confine the material, and then you, instead of pulling, you press because they don't offer strength when you pull them. And then once you do that, you can like build this strength-like curve. In the case of granular materials, this what measures the strength is called the friction angle. And you have this peak friction angle, and finally you have this residual strength. And at this point, the stage is called critical state, and the material starts to behave like a fluid. It starts to flow. And whenever you come in this first curve, we are coming from a very packed granular material, and in this second curve, we are coming from a very loose granular material. But the property is that if the material is the same, for instance, sand, it doesn't matter if it was packed or loose, you'll end up with the same residual strength once you go into critical state. And this state is characterized, it behaves like a fluid, so the material won't change in volume anymore. So it can behave like a fluid. In granular materials, there is a very, very tiny little elastic regime. You can sometimes consider that it depends on the kind of modulation that you're trying to do. But usually they go into the plastic regime very fast, very quickly. You have deformations and residual strengths and things like that. So now let me give you the outline. I'm going to try to do it like the less as I can. So I'm going to give you a brief introduction. Then I'm going to be talking about connecting the grain-to-grain interactions. Between the grains, you have contact forces. The grains have roughness, and they interact between them by the means of roughness. And you also have grain morphology. The shape of the grains changes from grain to grain. So there is a way of connecting the bulk behavior, this macroscopic or the engineering scale behavior, with the grain-to-grain interactions. So at this point, I was looking into theoretical mathematical expressions where we can squeeze some juices and get some physics out of them. And then we were into studying the effects of grain morphology purely into critical state. Here is in peak strength, the maximum strength that the material can reach. And finally, nowadays we're able to do X-ray tomography of samples of sand or any granular material. You can get the full picture of it, but once you do that, you have nothing else to do. So we've been able to develop a method where we can get those images and make the computational avatars of them and actually use those shapes of real grains for simulations. But the problem is that these X-ray machines are huge and expensive, and you need to study so you can operate these machines. And you cannot find them everywhere. And the samples that you can get to do those tests are very little, few thousand grains. So we are interested in going from the grain-to-grain interactions all the way to the continuum scale, to the engineering scale, to the field scale. But the samples with real sand or real materials are very small. So we were interested into developing a method which we have called cloning to generate based on the features of those grains, to generate new ones which have the same properties, physical properties, morphological properties. And then we're talking a little bit about that. And then some other related work, which is the work that I did with NASA. And my first master's degree was also in numerical methods, numerical analysis, and applied mathematics. So I have some work done in that field as well. And then I'll be talking about conclusions and some future work that you may be interested. So very briefly, you have this sample with any kind of granular material. It could be coffee beans, whatever. And you have the grain-to-grain interactions, interparticle contact forces, roughness, this red vector called the branch vector, which gives you an idea of the topology of the granular packing, the way in which the packing has been arranged. And we were able, trying to connect these two words, the continuum or bulk behavior with the grain-to-grain level. So this is the evolution of the strength. This is a property of the material called dilatancy. So these materials dilate. In metals, you can model, you pull the metal bar, and you can consider that if the deformation is small enough, it won't change in volume. But granular materials will change in volume always. So this gives you the evolution of the volume change. So here, we wanted to connect the Pigger strength, which is a macroscopic property, to the grain-to-grain interactions. Once the material gets into critical state, they have seen experimentally a lot of vorticity happening. It starts to flow, and you start to see a lot of vortices happening between the grains, and they call it granulence, but it's being seen only experimentally. So we wanted to develop some theory behind of that, trying to explain why it happens. And finally, at this point, the material doesn't depend on the interparticle friction anymore. So it doesn't matter if the grains have a roughness of 1 or 0.1. The material won't depend at that point. No granular material will depend at that point on the interparticle friction. And that has been seen experimentally. And we wanted to do some theory behind that. So strength. And here we have these two words, this big word, the macroscopic word is stress, and the microscopic, the grain-to-grain word for us is the grain level. So we wanted to connect them, and basically we're using here these two expressions. One of them is stress, shear stress that we call mechanics, the classic one. And this one comes from a process of homogenization in mathematics, where you can get the average stress of a granular packing in terms of contact forces and the fabric. So by combining those expressions with a constitutive model, that in this case, the most general, most basic model in granular materials is the Moore-Coulomb model, where this is a Moore circle, that this is basic mechanics. You plot the Moore circle in terms of the stress. You get the tangent, and this tangent, the slope is the so-called friction angle, which gives you the material strength. Then you can compute it. And by combining all those ingredients that I've been telling you, we're able to compute the friction angle, which is the material strength, in terms of contact forces, this branch vector, the fabric, and this is for general arbitrary shapes. Any shape of the grains, not only this, but any shape. So once we've got that, we want to study Pigger strength. So as I told you before, you need to confine the sample so it can offer some strength, and then you press the sample. And from the continuum level, from the macroscopic level, the continuum mechanics, we've developed these two necessary and sufficient conditions for granular packing in order to reach the maximum of the Pigger strength. These are nothing but the first-time derivative of the hydrostatic pressure, the pressure that you're confining the material with, and the shear strength. And by combining all these expressions that I've been talking to and doing some math behind, we've arrived to these summations that have to be maximum once the material reaches maximum strength. So what's the physical meaning of all this math? When you have a column, this column can bear some load till it buckles, it fails, it breaks, it buckles. So these summations being maximum, just as they are telling you that the packing is buckling at the grain-to-grain level as it is buckling at the macroscopic level. And it all has to happen at once. The shear force between the particles has to win over the compression between the particles. And then you need maximum of all of those forces at the local and global level. And this is some numerical experimentation in those terms. This is a simulation. the computer simulation is a polydispersed array. Polydispersed means that all the rings are different size. And we carry the tests around 2000, and this is the evolution of the strength. So the material reaches peak strength at more or less 3.6 axial strength. So all those summations should be maximum at this same axial strength as well, according to the theory that we were developing. And in fact, for the summations in global and local coordinates, we have that all of them reach more or less the maximum value at the same point, which is this red point here, for all those summations and components. So at least doing computer simulations, we've been able to prove that theory. So it seems to work, so the physical explanation of what it means must be somehow true. And now let's do the same thing with critical state. Remember, this is the stage where the material doesn't change in volume anymore, and it behaves like a fluid. And you can see all these vortices and so on and so forth. So we've been using a stress to study no change in volume. You better use strength, and you have this expression coming from continuum mechanics. And throughout an homogenization process, we've been able to develop this expression to compute the average strength rate of a given packing of granular materials in terms of the grain velocities and the fabric of the array. And you need this kind of boundaries to show this expression is valid, which we have called close-connected boundaries. And in terms of computations and math, they are really hard to find. But since we aren't interested in the math behind of that, but in the mechanics, we didn't go into that direction, but we used some tricks to compute them easily. And now we are combining these strength expressions that I'm showing to you with a constitutive model that includes dilation. So this is the dilation angle, and this is a Morse circle in terms of plastic strength. And you can compute the dilation angle directly from this Morse circle. So this is just a big picture of the constitutive model. Once you have dilation into the model, the plastic strain, the flow of the strain isn't orthogonal to the flow surface anymore, but it is orthogonal to a different surface, just to give you an idea. So now let's combine all the ingredients, and we get this expression to compute the dilation of the material in terms of like the grain velocities, the contact forces, and the interactions, strain kinematics, and so on. With this expression, now we can study critical state, which is when this dilation angle goes to 0. So that means the most general thing that you can like imply here is that that means that this numerator has to be equal to 0. So by doing so, it's equivalent to do the volumetric strain equal to 0. So the volumetric strain doesn't change. So that makes sense. That is critical state. And here you have this term, which is the grain velocity. This is the tangent component of the grain velocity, which has a translational and a rotational part. But if you combine these two expressions, you end up with this little expression right here that tells you that the translational part of the tangent component of the grain velocity has to be equal to 0 at critical state, which means that you are left only with rotational modes. And that explains why you have all this vorticity happening once the material goes into critical state and it starts to behave like a fluid. So you have these three basic mechanisms furnishing critical state, which is sliding. All the grains slide, for instance, around this blue one. With rotation, all of them rotate as one. And rolling, which is if you fix this one, the others will roll around this guy here. So this is the theory. This is the math behind all this solid behavior or solid kind of behavior. And now let's do some numerical experimentation. It's the same thing, around 6,000 grains polydispersed. And this belt right here is just so we can compute this close connected boundary that I was talking before. And this is the evolution of the material in terms of the peak strength for different values of the interparticle friction coefficient. So we compute peak strength for the same packing for different values of the interparticle friction coefficient. Also, we compute the maximum dilation, and we also compute the residual strength. So the claim was that once the packing goes into critical state, the residual strength that it offers, it doesn't depend on the interparticle friction coefficient. It becomes independent. And you can see here, more or less up to or from 0.4, this line, this green line here is kind of horizontal. And then we get into the math. We've got this expression by combining Coulomb's friction law, Hooke's law, and what I've been showing so far. And we use this one to prove, to analytically prove, to do math and prove that in fact this is true. And what? The proof is on the paper and so on. And this is the same packing that you were seeing before, but this is the velocity of the grain. And in particular, we have these two snapshots at critical state, and you can see actually the vorticity happening once the material goes into critical state. And for that, we have these, all these plots that numerically prove, and I'm not going to go into detail, but believe me, that shows that it works, at least from the numerical point of view. In general here, we have like found these necessary and sufficient conditions. Well, I don't know if you can think of it as convection. You might think of it, you may think more in mechanical terms, that you may think of it as a laminar flow, you know, or, you know, you have this Frost number in fluids that tells you if the flow is a laminar flow or if the flow is a turbulent flow. So these vortices might mean some turbulence since the material is behaving or starting to behave like a fluid rather than laminar. And it makes sense because, you know, granular materials are nonlinear everywhere. The shapes are nonlinear. The interactions are nonlinear. They are nonlinear. So it makes sense to have some turbulence from that point of view. And in the end, from the expressions, we can, the messages, the take-home messages, that you are left with no translational modes, but only with rotational modes. So that's the way that the material has decided to spend its energy. Must be the cheapest one, because materials are lazy, everything, nature. So I don't know if that answers the question. There's a way, yeah. In this world of granular materials, there is such a thing as an equivalent to a Reynolds number. Actually, we use this Reynolds, not only the Reynolds number, but the Reynolds stress that mainly comes from the grain velocity, and that is significant when the flow is very high, when the inertial numbers of the grains are very high. Otherwise, the Reynolds stress is really, really small, and it doesn't contribute if you are in the quasi-static mode. So we found these two necessary and sufficient conditions for maximum strength. We got this new expression to compute the strain rate in terms of particle velocities and so on. And we analytically unraveled the dominant microkinematical mechanism driving macroscopic behavior at critical state. And finally, we developed this proof, this mathematical proof of the independence of the residual strength on the interparticle friction coefficient. And now let's try to do something similar, but in terms of grain morphology. Now the variables aren't like kinetical or kinematical ones, are forces and so on, and velocities, but they are going to be morphological. So by now you must be familiar with this curve. We forget of this, and at this point, this is critical state. We have already proven that the material at this point is independent on the interparticle friction. But somehow, from material to material, this residual strength changes. So it must depend on something else, since it is independent. So it should be, or it must be, the shape. The shape of the grains has to be what makes them different from material to material. And there is no experimental or numerical evidence of that. There is only one paper, as far as we know, on that kind of, from the experimental side, proves this claim. And at critical state, we also have this line, which is the so-called critical state line, that is for modeling, and entire books and papers, and there's a whole school that is based on this critical state line, which has these two parameters, which is the critical state line slope and the intercept, which is this one. This is void ratio with, against pressure. So this is the way in which we classify grains in terms of morphology. We have roundness and we have sphericity. So sphericity is this guy right here, this circle right here, which is the order of the grain's diameter. And roundness is these guys right here, or order of the grain's diameter divided by 10. And you also have roughness, but we have already proven that a critical state the material doesn't depend on roughness anymore. So we forget about that. So now we are able to get the gray images of real grains and so on and so forth. And we have developed a computational method that's capable of taking those real shapes and making simulations. But we need, at this point, we were just coming up with that method, that computational method. So we need some calibration. And the calibration is this machine in Sydney, Australia, which is an infinite shear machine. It has two belts, and it will shear the material forever. So this is the original setup, and this is our numerical setup. And then we calibrate our model. This is the experiment, this is the theory, and this is our model. Once we have calibrated the model, we can throw this. Those are disks, by the way. So we know it works with disks, has been calibrated for disks. But now we can throw some real shapes. And we have these X-ray images from Caicos, which is a sand in France. We have these cross sections, and we throw them into this. And this is the numerical counterpart of the real thing there in Australia. And we have the two belts shearing the material, and so on and so forth. So we've been coding this for a while. And we've been working on integrating the Newton equations and so forth, and so on and so forth behind of this thing. And this is our own classification. We have these red grains or cross sections, which are actual real shapes. And these blue ones, which are equivalent in terms of this blue one has exactly the same roundness and exactly the same sphericity of this real one. But these are idealizations of geometrical forms, regular geometrical forms. So we have these two guys here, the red ones and the blue ones, because we want to study the difference of what is so special about real kind of materials. What if we can like just do these blue guys, which are equivalent morphologically? What will be the difference between the real and the idealized one? So here are some of the results. We have computed the different critical state parameters for the different values of regularity. Regularity is a morphological parameter, which is nothing but the average between sphericity and roundness. And you can see that the ones coming from the real, the line coming from the real grains, for lambda is different than the one coming from the idealized. The same thing for gamma is the other critical state parameter. And finally, for the residual strength, you have some resemblance between, they're kind of similar, but not quite the same. So in general, shape matters. Coming from the real thing is different than trying to idealize it. These are the results from the real test, from the real experiment, 3D experiment. And they claim that, for instance, the friction angle does depend only on roundness and not on sphericity. Gamma depends on roundness, and lambda, which is the other critical state parameter, will not depend on roundness nor sphericity. It basically doesn't depend on shape. We have plotted some contour surfaces for the different parameters and for the real and idealized shapes. And we can clearly see that even the values and the behavior of the surfaces are different. So it's not the same using the idealized ones and the real ones in general. Maybe here for the residual strength, they kind of behave the same in terms of values and the way that the surface behave. So in general, we have applied and used and developed this new method that allows us to use these X-ray images of real grains into the computer to actually generate some physical simulations. And we have used it to study the physics behind these critical state parameters and the effects of the idealization. Here's some physical findings that we have, is that the compaction becomes less pressure dependent as grain regularity increases. The more packing of grains, the more regular grains it has, you will need to put less pressure so it reaches maximum compaction, which kind of makes sense. If you have a packing with very irregular, edgy grains, you'll need to put an extra compaction to make it reach the maximum compaction. Regular grains reach the critical state with a more compact, which is a consequence of the first one stage, than irregular grains. And more regularity implies less strength. If you have a packing of spheres, it will show less strength than a packing with, say, tetrahedra, which will be stronger. Among all the parameters that we've been studying, we have found that in general, idealization matters. And this is the proof of that from the conclusions and the comparison with the only paper that we have so far out coming from experiments. And finally, let me talk about these cloning processes. So we're able to take the real sample of grains, get the X-ray images, turn them into numerical or computational avatars, and use them to do simulations. But as I said before, the samples are really small, and you cannot find an X-ray machine everywhere. So let's go to the X-ray machine. No, you can. No, sadly, you cannot do that. So since we want to do millions and trillions or whatever amount of grains, real grains, but the samples are really small, we were into looking for an algorithm that allows us to use the morphological parameters to generate new grains that satisfy the same morphology somehow. So basically, we have called it the morphological DNA. And we're going to be using this Martian regolith simulator provided by JPL. And we extract these parameters, the distribution for each grain, for the whole sample, aspect ratio, minimum principal direction, and rounded ratio. And over here, I have this volume to surface ratio that we are not going to include in the algorithm, but we use it to do some quality. So how do we extract the information from the grain, the digitalized grain? first we generated radius distribution by aligning all the grains with respect to their principal direction. You can compute like the eigenvalues of the eigenvector, the shape of the grain, and you align them with respect to their principal direction. You use a suitable spherical partition. You have a mesh in a spherical coordinate, say 8 times 16. And then you will have this LSD function that is a technology. And we convert it into spherical coordinates. And then we, for each point on the mesh, for each grain, we take the value of the radius. And then we get it consistently for all the grains which are different, that we get exactly at the same point what the radius is at that point, and the corresponding. Then the cloning algorithm is based in 3 steps: embryo conception, embryo development, and the final one is cloning. So the embryo conception is basically we use Monte Carlo sampling, which is a stochastic way of sampling from the distributions that we have already got from the real grains, the original. And we sample these parameters on aspect ratio, we Monte Carlo sample a minimum principal direction. We, using these two, generate a maximum principal direction, and then we uniformly, between these two, sample a mid-principal direction. With that, we compute, we are able to generate this so-called ellipsoid or embryo by being consistent with the spherical partition we use to sample the rate. Once we get this, we go to the embryo development, and we check for this point of the ellipsoid, and we sample from the corresponding distribution of radius. And once we have this, we turn that into this. And then we go ahead and we polish it for n number of things, say 1,000. We polish the whole thing till we get the whole sample of new clones. So this is how it looks in general, the whole algorithm. And these are some results. So we have parents, which are the real grains, and here are our clones. This kind of thing. I don't know. But also I have here some, so you guys are going to have to tell me which one which is the clone, which is the Which one? The left one is the computational one. Okay. Well, are you guys? You agree? Well, this is the real one, and this is the other guy. Same thing for so one of them is real, and one is computational. Yeah, this is a case where you can guess once that the computational ones sometimes some of them will exaggerate a little bit some features. And well, we call mutation the error by the algorithm. And here we have that for 1,000 clones that we generated from our original sample, and then randomly sampling from the original 1,000 original grains, we get the distributions of the morphological parameters, that's aspect ratios. So the means, you have some errors coming from the means, but the standard deviations are quite the same. In the case of roundness, the means are exactly the same, and the standard deviations are very similar between the parents and clones. In the case of the grains diameters, the same thing. Means are the same, standard deviations are very similar. And we were also able to build this curve that is very popular in soil mechanics, which is this fraction of grains passing a given sieve. And here you can get some of these parameters which are very useful for the soil mechanicians. And you can see that the two curves behave very similarly for those values. Finally, we're going to use this volume to surface ratio to check. We didn't use this property to get our clones. We are going to use this property just to check how well are we doing whenever we are aiming a given property. So yeah, the standard deviations are kind of bad, but the means are similar. So we kind of nail it as well. So in general, here we computationally obtain these morphological properties, roundness, sphericity, which was a challenge by itself because it hasn't been done computationally. How you do it is by experimental means. Is a technician that kind of has some experience and looks at the grains and says, well, roundness is more or less this, and roughness and sphericity. There's no an algorithmic process actually to compute it. So it was a challenge by itself. And then we developed this algorithm that we have called GSC, geometric stochastic cloning, that can actually be used for cloning other kind of stuff as well, not only grains. And we generated this pool of clones, and we compared the accuracy. And finally, we analyzed the dropouts and the potential improvements of the algorithm itself, by itself. So now, some related work. Mm-hmm. Yeah, okay. No, the real sample, for instance, remember the other part where we were studying the influence of grains morphology and critical state. And I mentioned it was Caicossoid, this sand from France, because in France they have the X-ray machine. So they take the images and they send, they don't know what to do with those images, and they send it to us, and we try to do something with that. And for the clones paper, we were using which one? Oh, the Caicossoid, but it was provided by the French guys. Yeah, it was provided by them. We didn't have. For the clones paper, it was our sample. It was regolith simulant, Martian regolith simulant, which is a simulant of Martian soil that they prepare at JPL. And then we ship the samples from Caltech to the French guys, which got the images and send it back to us. And then we work on that. Yeah, and so that is a real material. It's been prepared to behave in such a way that they can consider it to behave like Martian soil. Yeah, but it isn't actually a Martian soil. No one has been able to bring back a sample with Martian soil so far. And that's when it comes into the picture. So this is a project that I was working on 3 years ago together with JPL and NASA. So the idea was developing this device to perform a shear test and a sinkage test. So as I mentioned before, Spirit got stuck into Martian soil, Martian sand, and now they were really worried about getting the next rovers stuck as well, which are more expensive and more expensive over time. So the idea was having the rover to perform the test. So usually what we cannot do on Mars is have a guy sampling. We cannot ship it back, even if we don't have a guy sampling. We cannot ship the sample back to the Earth. That we cannot do. So the only thing that we can do, so we can like rob Martian soil and build structures on top of it, is have a robot or a rover performing the test by itself. That here on Earth is a big deal. No one does that because usually you have a lot of disturbance in the samples and so on and so forth. And the equipment to doing in situ testing is huge and a lot of technology going on. So they wanted something as simple as possible in terms of technology. So they can get an idea of the materials strength, and also these Becker parameters that can give you syncage if you want to rob or have people walking on it or other kind of vehicles going around Mars. So we developed from scratch the device, trying to be as low-tech as possible. This is the design process, the calculation process, and then we went into actual testing. And these are the results. We had actually pretty accurate results, especially for the part of the friction angle, which is the materials strength. For the Becker parameters, we were able to get some stuff, but we didn't have something to validate. We didn't have enough data to validate what we got. So it might be right, it might be wrong. We don't know. So in this project, we went from designing the experiment, and here we have a video. It's a SolidWorks file. It's a simulation of the design process. Just of the device, we have this trigger. The rover like pushes with its own weight on the box, which is inside. The trigger opens these flaps that clings around, and then the rover can perform the test. You have this box that is inside of the whole mechanism. Everything is mechanical here. We only have a cell force measuring the force, and that's it. That's the only electronical thing that we have here. And then we went into prototyping and building it. And here's a video. We were using some mechanical pushing, and here we have the cell force measuring the force. And you're gonna see in a minute the box. Here, I'm going to show the video of the box testing, how the box was working. So that's the box. This is at the shop. And you're going to see it moving. So it's taking some time. But well, see, now it's moving. The movement has to be very, very slow, very, very subtle. It was just for the testing of the box that goes inside this device. And here the force cell just collecting the data, giving you an idea of the force that is being exerted and building the curves that I was shown. And this is part of the thing that I've been working on with, it was the Keck Institute for Space Studies, JPL and NASA, which is the same thing. I got my first master's degree in numerical analysis and computational and applied mathematics. And I was working a lot on that. So this is an equation that I used to work on, is the advection diffusion reaction equation. It's a particular case of the Navier-Stokes equation for fluid. And the problem is that you can discretize it with this is called the weak form for finite elements, if you want to discretize it in your computer. And you can get three different weak forms in these Hilbert spaces. But once you apply the finite element method with mesh, you don't get this kind of solutions. The method just blows up. It doesn't matter which weak form you're using. So I was working on stabilizing these weak forms in such a way that by using finite elements, you can still get a good solution. The method converges. And that was studying where the solutions can live in terms of functional spaces. So you have these Hilbert spaces, you have Lebesgue spaces, and Sobolev spaces, and we were trying to guess a method that we call the orthogonal subscales to improve the solutions with numerical methods. These are some publications on other works. This is the one with JPL, some work on granular materials that I've been doing on the side, publication in numerical analysis in the book that I got to publish with Avi Ayala in Quito, which is a very well-known publisher here in Ecuador. So I have here some conclusions. You already guys know the big picture, just if you have some questions asked. about the general work that I've been doing in these last years, and some future work that I could be doing related to that, which is mainly expanding that knowledge on those axes that I've been showing to you. And that's pretty much it. If you guys have any questions.
So the rover got stuck, and did it get stuck because it started to sink in the granular material? Did it get stuck because it couldn't move? Because maybe there was a rotation of the granular material? What do you think? Why do you think it got stuck in? What do you think?
What actually happened is that they were like driving the rover from Earth. It takes around 8 minutes to the signal in order to go and come. But they were driving the rover from Earth, and it was a normal day, one more day. And suddenly this thing got stuck. And apparently they got the rover stuck a couple of times before, but they were able to pull back a little bit, move the wheel, and somehow managed to get it out. And that day they couldn't, and they had no idea. It apparently from the cameras, from the images, it was the same material, the same thing as the rest of the path. Well, it might be different things. It might be that the material at that part of the path was actually different inside, and from outside it was looking the same. It was looser rather than more packed, dense enough. Or it could go to a bad driving thing. So they didn't do the proper thing that day as they did the other days to get the rover out. And every time that they were trying to get it out, they were making it worse and worse and worse. It was sinking more and more and more. So of course,